Welcome everyone. My name is Albert Cohen. I would like to present some work on the interference between compiler optimizations and the properties of secure applications. This is joint work with colleagues from Sorbonne Université, ARM, and ST Microelectronics. So let's look at a very simple example. The phenomenon known as within weeks, what you see is not what you execute, is very well known by security experts. Let's take this example from cryptographic applications where a key has been masked by some random noise M. Masking is used to make sure side channel attacks or cyber attacks would not be able to reveal the secret key, the plain secret key. And when communicating across modules of a secure application, you may have to remask or change the mask of the secret key. And for doing that, you want to make sure that you first mask with an additional blank noise mask, let's call it N, before unmasking with M, the original mask. And this is what happens on the right. On the left, what happens is typically compilers don't have to respect the ordering prescribed in the C source code. And the intuition is reasonably simple. We want to observe intermediate values of computations, as the example shows, and we also would like to make sure that those observations take place in the prescribed order. So that typically means that we need some kind of first-class observation function. And of course, we also would like this observation to be opaque to the compiler. Why is that? It's because we don't want the compiler to reason on the values of the variables being observed. Otherwise, in this case, it would defeat the purpose. If the compiler was able to check that T1 is the result of a XOR, which is associative, then the downstream operations may also take into account this property and essentially reshuffle the operation, even if the observation was preserved. We may still unmask the key. So we would like these properties to be principled, as I said, both the preservation and the fact that it is made compiler independent are key objectives, and we would like to understand better what are the constraints on program transformations that result from this goal. So let's look at a few more examples. One of them is also very simple. It's an example that derives from prevention of fault attacks on the control flow. So it's a form of very fine-grained control flow integrity, where a counter is incremented in between every two operations, even two instructions of the source program. And in this case, you would like the compiler to preserve this interleaving, this ordering of instructions. Of course, compilers don't have any such constraint in general, because the counters are completely independent. If you look at line 3 on the left, C and T++ is independent of the previous assignment or the previous definition, and there is no reason optimizations would preserve this particular ordering. So using opaque observations, the intuition is that we can chain those observations such that the interleaving can be forced by spurious dependencies. Think of some tokens, some control tokens that would embed the ordering constraints into the data flow of the program. And in this case, the counter CNT is made to depend on the previous definition of A, which itself, of course, depends on B and C, but specifically also depends on the initialization of CNT to 0. And this is something that is quite easy to think of as a security expert. As soon as you want to observe a value and you want those observations to take place in a particular order, just insert the additional dependencies you need through these observe functions. Another example, slightly more complex, you may want, again, in the cryptographic application, to erase buffers that have been storing secret data, sensitive data like secret keys, etc. And this is pretty common in secure implementations of crypto applications, except that, once again, like a mem set with 0, which would typically erase the data, does not bear any dependence with other parts of the computation. For example, there is no reason this mem set would take place at all on a buffer that would be dead at the end of a function, like this secret buffer here. The compiler can detect that this memset is dead code, and typically optimizing compilers do that. So one way of preventing dead code elimination in this case and proper ordering of the memset is, again, to insert an observation of the secret of the buffer by mandating that this observation takes place after the memset and before return from the function. In this case, the last part of the constraint is implemented by some dummy I/O operation that simulates something that the compiler has to preserve, the fact that some I/O takes place at the end of the function. And this, the challenge is particularly difficult, as I mentioned, because we want it to be future-proof and robust, in the sense that we don't want to restrict a priori the set of transformations that a compiler can implement. We want our approach to be robust to any existing or future transformation that preserves I/O. And this is captured by this notion of an event map that relates events before and after transformation for an arbitrary transformation. And the only thing that this event map must contractually preserve is the mapping between I/O events before and after transformation and their partial ordering. And this is what we assume existing compilers do, that preserving I/O and the ordering of I/O events is guaranteed by valid program transformations, and so this event map would be maintained, would maintain the connection between I/O events before and after transformation. But we need to grow this event map beyond I/O. We need to also model arbitrary instructions when they need to be preserved, including observations. And that's what we're going to do next. And the first thing we need to do is to make sure that the trace of the state machine of the semantics is extended to model the partial state that's captured by observation. So we want to make sure that the state machine isolates the values that are being observed in addition to the I/O. And we are going to define partial ordering on observation events, very much like the partial ordering on I/O. We are going to call it happens before relation, which is grown from the I/O ordering itself, of course, but also any events that relate an observation with another like definition or use, and observations themselves. So any dependence that relates an observation with something else, or observations among themselves, will also be part of this happens before relation. So this is very classical for memory modeling, for example, in concurrent semantics, shared memory semantics, and we borrow the same principles, same principles here. The problem is, now we have a well-defined happens before relation that we know the compiler has to implement, has to respect, except that compilers don't know about observations and don't know about this happens before relation. So we need somehow to make it learn about it and make the compiler preserve observations despite that. And so there is a formalization that basically takes two steps for these properties. The first one is some form of upstream preservation. Is that the event map, the map that talks about the preservation of events before and after transformation, has to preserve dependencies between observations and uses of these observations. So if you have an observation that's being used in the original program, after transformation, it should still be there, so it should be preserved, and there should be a dependence from the transformed observation and subsequent uses. So this is what the formula says below, but I won't dig into it in detail. And you have some form of symmetric property. This is an opaque value. It must also transform into an event that uses this value. So that means there is no way for a compiler to guess the value of an opaque observation. If it was able to guess, you can always speculate on it, but eventually you have to verify that this is the correct value. If the compiler was completely able to guess the opaque values, then it would defeat the opacity purpose. And by doing that, essentially we have the instruments for building the chains of opaque observations we mentioned on the examples before. So we can chain observations to downstream I/O, so that's a way to enforce their preservation, so they cannot be removed, otherwise the I/O would not be able to read transitively the proper, read or write the proper values. And we can also implement this happens before partial ordering on observations and anything that is in dependence with observations. And so there is a theorem that proves that formally, leveraging these two constraints, 1 and 2 I just showed, and chaining observations along these lines. And so to establish this theorem is actually quite technical. The reason is that compilers are super smart and can be super smart at guessing values when control flow or data flow reduces the amount of information that's in the program. So it's really like an information theoretic problem that we have here. For example, data dependencies can be converted into control dependencies and vice versa. So we cannot only consider data dependencies when establishing these opaque chains. And like constant specialization can break dependencies. So you may have a chain of dependencies that can be broken when the compiler realizes by static analysis that a value is always 0, for example. And then that defeats the purpose of chaining the observations to enforce some form of preservation or happens before relation. Same thing with instruction combinings, like merging of equivalence instructions also can break control dependencies. So there is some information preservation hypothesis here that needs to be added to the notion of dependence chain to form these opaque chains. So again, I cannot go into the formal detail of this, but this was one of the big contributions of the paper. And thanks to this theorem, we can actually implement a preservation mechanism for opaque observations in Clang and LLVM and prove that this implementation is robust, not only for a particular version of LLVM, but for future ones as well. So the implementation leverages metadata and built-ins with very minimal changes. Actually, only two main instrumental functions of LLVM have to be modified to deal with the proper handling of this metadata. And we can also encode observations as an extension of object code of the dwarf format, so that like monitors or debuggers or binary analysis tools can actually check that the observations are still there in the generated code, which is also something we want to do in secure applications. So we implemented two kinds of validation procedures. A functional validation one that essentially checks the presence of observations, so their integrity and ordering, and the integrity of the security countermeasures as protected through these observations. So I won't go into detail here, but this is essentially checking that everything is there and properly ordered. And also performance evaluation, because in the end, all this mechanism makes sense only if performance is better than unoptimized code or also some of the state of the art. So aside from the compiler tricks I mentioned, I'd like to mention some recent work where we also proposed an automatic mechanism for dealing with that problem. But that problem, the mechanism was much more heavy on performance by inserting I/O barriers every time we insert an observation, and also lacked a formal formalization and proof. So we evaluated performance on 9 security applications, ranging from the erasure of secret data that we have seen and key masking or remasking, also some control flow oriented protections that are meant to protect against side channel attacks or fault attacks, and so both at the loop level and at the level of individual instructions, and also to help implement time-insensitive selection, like constant time selection, to also prevent side channel attacks in crypto applications. So let's look at the first batch of results. So the 9 applications are listed on the bottom, and the bars correspond to the performance, the speed-ups of successive optimization flags, so O1 to O3, and 2 optimization flags for size, OS and OZ. And the baseline is here the unoptimized version of the application. And we compare on 2 applications for the first 7, and also on 2 hardware platforms for the first 7 applications, and also on IA32 for the constant time applications. So both ARM x86 64 are like represent essentially low end and higher end machines. The IA32 target is here to represent a case where it's known that compiler optimizations would actually break the constant time property of a secure implementation if it was not modified to do it. And here we propose an alternative portable way to achieving the same thing without tricks. So the speedups can be quite significant, but again, this is compared to unoptimized code. So that's mostly like a sanity check that we are indeed capable of optimizing code in presence of opaque observations. The second batch of experiments are the same speedups, but this time the baseline is either the compiler tricks for the constant time or the state-of-the-art implementation using I/O barriers every time an observation is mandated. And here again, we do observe pretty significant speedups in some of the benchmarks like mask rotate or SCI pin, and more minor improvements on others. Just to conclude, in a nutshell, so we have seen that this within weeks phenomenon is a typical representative of this interplay between optimizing compilation and security properties, and we proposed a portable and robust method to extend the compiler correctness guarantees, like the validity properties of program transformations, to the notion of opaque observations that are much lighter weight than actual I/O. We show that we can implement these fine-grained and indirect control and optimizations without much impact to a production compiler. We propose also the first formalization and correctness proof of such an approach. And we did confirm that the performance was there compared to the state of the art. So there are interesting perspectives as well I would like to mention. One of them is while this paper was focused on security applications, there is a lot of interest also from a software engineering standpoint, where implementing monitors that are very low overhead, like without actually instrumenting the code with checks all over the place, and doing this on optimized code as well, can be very interesting in terms of debugging and testing. And that's something we'd like to investigate in the future. Thank you very much.